Swayam Prabha. Digital India. Educated India.
So, one thing is like time intervals matters like in most cases and in most scheduling problems. For instance, if you are assigning classrooms or lectures, right. So, then suppose you know that a particular lecture, say math lecture or not, this is for say lecture by say Professor A, has to happen at 10:30 to 11:30, right? And because he will come at that time and then he has to give his lecture and go. And another person B will give a lecture at 9 to 11, 2-hour lecture, and another person C will talk from 9:30 to say 10:45 or something like that. So, several people have to, so your duty, maybe you are a program organizer or something like that, and you have to schedule all these lectures. I mean, where, which room they have to, you have to find room for that, right. So, each person is giving a lecture, and what is important is his time is fixed. He is not going to ready to change the time in which, because maybe that is part of other program. So, he wants to go somewhere or he is not ready. So, this is the final thing, and you have to find classrooms for this. It is very clear that 2 lectures cannot happen at the same time in the same place, right. So, therefore, so what we can do here is each lecture essentially is the time interval in which it is happening, right. So, we can say yeah, we on the real line we can mark it. So, for 10, so the first lecture A is from 10:30 to 11:30, right. This is A, and B is from 9 to 11. So, 9 to 11, like that, because that is the interval. And then the other one I told from 9:30 to 10:45, right, 9:30 to 10:45, yeah, somewhere here, 10:45. Like that you can associate with each lecture a time interval, right. Then you can construct a graph for this if you want, right. So, for instance, so there can be so many of them, so you just quickly construct. So, whenever the intervals intersect, you put an edge between them, it means conflict, right. So, two intervals means 2 time intervals are intersecting, means you cannot have this same room for that lecture, right. You should find 2 different rooms to this thing. Otherwise, at 9 o'clock you started one lecture and it will go on till 11 o'clock, but somebody will come at 9:30 and you want to start a lecture, there will be conflict. So, you can draw this graph, and this is the interval graph corresponding to this conflict, right. And now what correspond to the number of minimum number of classrooms you need for this? Maximum degree means some among all the intervals, how many other intervals are intersecting with it? What is the correct parameter which we are looking for? What kind of lectures can be scheduled in the same classroom, non-intersecting? In terms of graphs, what that means what? What is the parameter? It's independent set, right? An independent set of vertices which correspond to certain intervals, right? Those intervals corresponding to an independent set of vertices can be scheduled at in the same classroom, because there is no conflict between them. So, that means which is the minimum number of classroom correspond to, you have to book these classrooms, no? So, how many classrooms you have to book then? Minimum number of classrooms corresponds to what? What parameter here? Minimum number of colors required. Vertex cover, it all because you heard about vertex cover in the last class, right? So, it is a color because each classroom correspond to a collection of lectures which don't conflict with each other, they form an independent set, right? Essentially, you are covering the set of vertices with these independent sets, right? Each independent set is a color now, right? So, color class. So, therefore, minimum, that is a coloring problem in fact. So, though it looks like a very different question, but it is it's actually a coloring problem. The number of colors, this number of colors appears in many such problems where we are trying to minimize a resource. Here resource is the number of rooms, right, because that is what people are coming, and then we have to book the rooms. Each room will cost something, right. So, we want to reduce the number of rooms. We can't book, maybe the seminar hall costs a lot of money, who knows, you can't book unnecessarily, right. Why unnecessarily book a room and waste money, right. So, that is essentially it is a colors, right. So, this is an interval graph coloring problem in that case. So, I just this is just a toy example, but still you will get a clear idea that this is going to be very useful, right, because if there are many lectures and many things, it will look very complicated. How will you just figure out what is the minimum optimum number of classrooms? So, once you identify that it is a coloring problem and it is an interval graph coloring problem, and you know in caudal graphs coloring is a very easy problem, right. You saw a linear time algorithm there. So, you can very easily solve the problem. You do not have to like apply your brain so much. You have all the tools at your disposal. So, just that you have to systematically think and make use of the tools we have developed, right. Otherwise, also probably you may do it with 50 lectures at the same time, and then you may try to work out, and then sometimes, but you yourself will not be sure whether you are doing it properly or not. Actually, you have got the exact number or not, right. So, you may end up booking an extra room or something like that, right. Do you agree with me? Sometimes it is very likely to happen. So, but here you have a correct solution. And see, this is about scheduling, looking for rooms or conference also, whatever. I can also tell you a very like simplified version of a question which find in computer science, right, in designing compiler, part of compilers work and all. So, when you write a program and then give it to a compiler and it compiles, and what it generates is an intermediate code, right. How many people know a little bit about how the computers work and all? Compilers, you know, and there is an intermediate code generation, right. So, it is like first, so many a sequence of instructions will be written, right, A plus B equal to C, these are all like registers and all, right. So, typically what bad programmers do is they start writing a program, and then first they do is to define a lot of variables, right, like because they do not know what they will need, and then they write so many variables, and then they keep assigning, and then they forget about the variables with the thing, and then they define something else. This is what. But the compiler has to worry about all these things. Why? Because all these things you are storing in the variable, it has to keep, finally when it was to use it in the, it has to keep it in some registers, right. But because it goes into the register, and then these registers keep those values when this kind of machine language instructions add up whatever is there in the file. But because the registers are high speed thing, so because it is not like keeping in your disk or hard disk or something, it will be much costlier, right. And also it should be in a small processor, right. So, therefore, that will, you cannot have too many of them, right. There should be small numbers, right. So, naturally we cannot use too many registers, because others also will need the same thing, right. So, that is a resource. So, what happens is your variable suppose some x comes first in the second instruction, say here it first starts come into life, that is a lifespan or something like that, right, and then it goes, and after 11th instruction x is never used, the whatever the programmer just forget it. So that means the compiler has to understand that beyond this x is not required. But on the other hand, there is another variable y here which started at the instruction number 6, but it goes all the way to say instruction number 15th, right. So then it is something like this, right. It beyond that, before that it is not used, after that it is not used. And then there can be another variable which comes from instruction number 100 to 200, right. So there is an interval which correspond to each variable, because that is the duration in which the instruction first time it appears and last time it is used, right. Beyond that you do not have to keep it in a register, right, you can forget it, you can release that register, right. Now you see that for each variable you have an interval there, and which variables can share a register then. So here x and y cannot share a register. Why? Because x is from 1 to 11, but in between y comes, right. If I am using a register for x and also for the y, then how can I keep the value of x and y both in the same register? But if y comes later after 11th instruction, then always I can delete x and put y in that, right. So you can see a natural interval graph here. The vertices will be the variables, right, and each variable correspond to an interval, and whenever the intervals intersect, right, then you have to put an edge between the variables, right, otherwise you should not. So that is an interval graph in fact. Now what is the minimum number of registers required for this case? Because what kind of variables can be can share the same register? One register corresponds to a collection of variables which do not overlap in time, right. So therefore they are the things which form a what in the graph, that form an independent set in the graph, right, because they do not intersect with each other, there is no conflict. So therefore register becomes a color then, right, each register corresponds to a color. So I do not know whether most see, if you have not seen this intermediate code generation and all, if you have no idea, then probably you might have missed it, but those people who have seen it will probably understand this, right. It is a simple thing which I have told, but that should make you aware that though this is a very simple example, story examples, just to make it. So usually there will be some jumps and all here and there, so it will not be so simple, but even then you will get the idea here, right. This coloring is, though it is a fancy thing, though it may look like somebody, some painter has defined this problem. Yeah, it is. It was defined by, so maybe the map coloring problem, or somebody was trying to color the map of some countries, and then they showed that. So they saw that only 4 colors are required, right? So this, it's really it was a coloring problem there, but again, coloring is not always that colors. In fact, there is no paint and brush all the time. Many times it gets translated to very useful stuff like resources, right? Color is a resource, and it is something like how many rooms you require, how many registers you require. So essentially cost, right? You are trying to reduce them. When it tries to minimize the number of colors used, you are trying to minimize the amount of money you are spending, right? So that is what you should understand, because when in your class the coloring problem is sort of very natural to think that it is only a fancy thing, it's for fun, it is for because anyway it's colorful, it's nice, it's elegant, it's beautiful, but beyond that there is it's something which has lot of potential in applications, right? And at least with the interval graphs you can see that this coloring problem turns out to be very, many times these problems come with a little extra. It need not be a very nice interval graph, but maybe some extra will be there which you can figure out usually, right, in real problems, right. but at least the basic things you get to see that, and then you see that this is a very, though the chromatic number problem, the coloring problem is usually NP hard and difficult to tackle, but in these kind of graphs, special class of graphs like interval graphs, it's quite easy to do, and it so happens that really in applications it seems to be this kind of simple structures, right. That is the good thing about like though they are very that told NP hard and all, when we deal with something we usually have some structure, right, some extra structure which helps us to deal with the problem in polynomial time or more efficiently, right. So, this was just to motivate this graph class and also the graph problems beyond the jugglery of mathematics that we do in class, right. So, there are useful things that we can do with it. Anyway, interval graphs are, the key point is interval graphs of intersection graphs, and these intersection models are like when it comes to special graph classes, this intersection graph is a big concept, because many times we end up seeing intersection graphs, and they are mostly very useful stuff. And first question I can ask, because I came from caudal graphs. So, does caudal graph have an intersection representation? Is it the intersection graph of something? Probably we should ask that question before moving on, right. So, it so happens that anyway caudal graph is the interval graph is a subclass of caudal graph. So, there should be something similar in caudal graphs also. It so happens that using trees we can get an intersection representation for caudal graph. It is something like this. Suppose I draw a tree. And then now this is whichever tree you want you can make, and then you consider some set of subtrees of this tree. Yeah, maybe this is a subtree here. I can make another subtree here, just another here. Like subtree means it is a should be connected. So this is a subtree, this is a subtree, but not if I draw. Suppose I draw something here, and then I try to draw something here. Then it is not connected, right? It's two pieces. So, only connected pieces we consider as subtrees. So, the connected subtrees I can say if you are confused, right. So, now let us say this is a subtree. So, there is some intersection here, and then there is another subtree I can draw like this, right. Now, for each of these subtrees you can associate a vertex, and if they are intersecting between each other on some vertex, and then you can put an edge between them, and then you construct a graph like that. Now, my claim is that if you do this thing you will end up getting a caudal graph. Is it easy to see that? So, the caudal graphs are intersection graphs of subtrees of trees. So, can you make a 4 cycle? I think you should think about it. So, why if I make this thing and then make the intersection graph from this thing, it will make a caudal graph. But let us get an idea about this thing by again making use of the perfect elimination ordering. The what is a maximal clique? Of a graph. So, you take a clique, suppose this is a clique here in the graph, and then you see any other vertex, whether can it be added to the clique. That means, if all the vertices in this clique is connected to them, then you can extend it, and you see any other vertex is there outside which is connected to all the vertices here, then we can make it be even bigger, right. At some point of time you will have to stop. So, that means that you it is maximal. That means, you cannot make it bigger by adding a new one, because if I take any other vertex, it may be connected to this and this, but it may not be connected to this, right. So, or maybe some other vertex, it may be connected to this and this, but it is not connected to this. So, there won't be a new vertex which can be added to it such that the new graph is again a clique. So, then we say that it is maximal, again maximal, not maximum. What is maximum then? Maximum means in terms of the number of vertices which should be biggest, right? Maximum is maximal, but maximal need not be maximum, right? So, minimum is minimal, but minimal need not be minimum, right? So, we think of maximal cliques. Now, let us try to construct a structure using maximal cliques of caudal graphs. This we will do using the perfect elimination ordering. We will, so suppose this is the perfect elimination ordering V1, V2, V3, Vn. Now, like we did in the coloring, we start from the last to backward, right. So, we consider Vn then, and then we will just put Vn in a bag and put it there. And then we put V2. So, if V2 is separate, we can put it separate, but if V2 is adjacent to something, right, if you look at the neighbors, if V2 is adjacent to V1, then we will put V1 and V2 in the same bag. So, what I am going to do is to construct a tree structure of bags, something like this, maybe something like this. So, in this thing there will be many vertices V1, V2, V4, V10, V11 like that, many vertices, each one will contain. The property will be that each of these bags will be a maximal clique. So, if you look at the bags, that will be maximal cliques. And it will also satisfy the property that if you look at the maximal cliques in which a particular vertex, say u appears. So, u appears here, u appears here, u appears here, that will form a connected structure in the tree. So, it is not that u will appear in these three and then u will appear here, but not here, that will not happen. So, this is the thing that we want. So, for this purpose, so we use the perfect elimination ordering. So, we keep constructing like this. So, when we consider the next vertex in this reverse order of the perfect elimination ordering, ith vertex when we consider, we look at its neighbors. Luckily, we know that because we are considering it in the perfect elimination ordering, its neighbors in the already considered set will be a clique. That clique, it may so happen that it is, so you will identify it somewhere now because it is a clique, right. By till now inductively you can assume that till now we have satisfied all the properties that we want, right. For all the bags that we have created till now is a maximal clique, right, and the other property also is satisfied. If you look at a vertex u and identify the maximal cliques in which it is part of, those bags are coming connected, right.